Welcome back, lecture 7.2, where we're going to talk about Joule's experiment and heat. So, just sort of as a historical note, right? This Joule experiment is relatively an interesting one to consider. So what we talked about last time was all these interchangeable forms of work, as long as they were configurational, but we couldn't count in descriptions of work any that were dissipative. So the nice idea there was thinking about the charging an inductor or charging a capacitor were okay because those were reversible, but having current flow through a resistor and dissipate power wasn't okay. Right? So we all have heard of Joule because of the unit named after him and the unit of energy, right? So we're going to really be thinking about energy today, and your book takes a very historical point of view and really thinking, not even assuming that we know about conservation of energy. Let's take a slightly more modern approach and just go ahead and realize that we understand that there should be conservation of energy. Most of you are, you're third-year physicists now, and you're pretty comfortable with the idea that energy should not be created or destroyed, only transferred from one medium to another. We're going to really see a really nice example of that today. Okay, so Joule was a brewer. Brewed presumably beer, but definitely alcohol, right? So this is kind of fun, and if you've ever seen, actually craft brewing has exploded in Alberta, and I'm a big fan of a lot of these craft breweries. And if you've ever actually seen some of this equipment, you'll see it'll kind of look familiar. So brewer was basically had access to this equipment, which was brewing equipment, which I'm going to attempt to draw something like it now. Okay, so the first thing is that he would build nicely insulated chambers for his pre-beer. I think it's called the wort, but that doesn't really matter. So imagine building the following experiment. You have a sealed container, and now this is sort of an axle or a rod, and you add some paddles to this. Okay, and you put a thermometer in here to measure the temperature. Okay, now what he found was that, for example, you could add a certain amount of work, right? So move this mass, and with a force mg through some distance dx, right? Or delta x, and what you would do is you would spin these paddles, right? And during that spinning, you would generate a certain amount of heat. So to first order, let's imagine that our wort is just water, right? It's just a material, it's just a liquid, right? And we're going to measure the temperature of that liquid. Okay, so this is what Joule did, and he found two particular things. If the walls were insulating, aka adiabatic walls, right? And even though you're doing something where the work looks like it should be reversible, if you're doing this dissipatively, right, you go from a configurational work to a dissipative work, they actually found that the temperature of water goes up, right? Okay, so this is actually, it seems very obvious to you, but it's actually not really clear historically that I can turn something like configurational work into temperature. I've now linked up work and temperature in an unusual way, right? Furthermore, it was repeatable. It was quantifiable. Could measure how much the temperature went up for a specific amount of work you put in, and it didn't matter how you added the work. It didn't matter how you added the work, it only added how much work you added to the system. Okay? So Joule's findings were the following. So one, it always took 4.2 kilojoules, so 4.2 thousand joules of work to raise the temperature of 1 kilogram of water by 1 degree. And we're going to say 1 Kelvin. Because we're going to do SI units. And to this point about kind of work didn't matter. Didn't matter how you put that work in, you got the same answer. Now that's really interesting because they didn't at this time really understand that all forms of energy and all forms of work were the same, but we, on the other hand, do, right? We know that all of these things are going to be forms of energy, right? And moreover, we're going to have the conservation of energy. So this is really leading us to this understanding of the conservation of energy. So we know it and we're comfortable with it, but they weren't, and now this is leading it to it. Okay, so how do we state the conservation of energy mathematically? Okay, so let's call the internal energy of the system U. Okay. Now, energy is very curious because I never know how the zero of energy, right? You know that the zero of energy is arbitrary. I don't know if this thing has this, I can never really see all of the energy something has. So, for example, we talk about the energy of any system here in the room, but we never really take into account the kinetic energy of the fact that we're rotating around, spinning on the Earth. right? Or that we're moving through, the Earth is moving around the sun. We don't always think of all the various sources of energy. The zero is arbitrary. As long as there's some definable background, what we really care about are changes in the energy, right? So we're going to care about the changes of energy in the system, and we're going to have the work, right? This is our configurational work that we've been talking about. And we're now going to name our dissipative work, right? We're going to name our dissipative work as heat, right? And we're going to label it with Q. So our statement of conservation of energy is that the change in energy is going to be really the work plus the heat, right? That is that work and heat in the form of temperature rising, are equivalent forms of energy, and that can be added together to find the total internal energy. And this is so important. This is called the first law of thermodynamics. It is not the form of the first law that we will typically use. You'll see the form that we typically use in just a second. Okay? And so that means that the internal of the energy of a system can be changed by either changing its work or its heat or both, right? So this is going to be by mechanical things, by doing displacements, changes in volume, changes in length, moving over distances. And this one, the heat is going to come from temperature differences. Okay. So there's a sign convention for heat, just like there was for work. And it's going to be that Q is positive if heat flows into a system. Okay? That's very similar to our work was positive if done on our system, right? So if heat flows into our system or we do work on our system, then our signs are going to be positive. Okay? So this is very much the way we have defined the heat. Okay, so this is the sign convention for heat. Okay, now this leads us back, continuing to think about heat. Oh, actually, I'm going to take a second, and I'm going to hopefully splice in a little video of, if I can find one, of those brewing vessels where they mix up the wort. If you haven't seen one, I hope to find one, a video, and show it and splice it in. Okay, so now with work, we often cared about finding dW so that we could integrate to find the work, right? So for an infinitesimal change in U, we write du is dW plus dQ. Okay, so this is the form of the first law that we're typically going to start with. Okay, so a couple of notes. U is a state function. That means it only depends on its thermodynamic variables, right? So if I define the thermodynamic variables, I've defined the state. And hence, du is an exact differential. Just like before when we had dv, dv was an exact differential, and therefore we could write down our exact differential. You know, dv was partial v partial p is constant t times dv plus partial v partial t at constant p dt. Or maybe I said it wrong. Right? Likewise, u is a state function, hence du is an exact differential. But dw and dq are inexact. That's because w and q are not state functions, hence dw and dq cannot simply be defined in terms of the thermodynamic variables, right? I need to know the path I took, right? And that's what these little bars over the d's mean. These are to indicate that we are dealing with an inexact differential. All right, now, so u is a state function, but there's an interesting point, right? So u as a state function means I can write u, for example, in terms of thermodynamic variables, right? I can write it in terms of v and t. I could write u in terms of p and v, right? It could be a function of any two thermodynamic variables. But curiously, I cannot use my equation of state to arrive at u, right? A good example of that is if I have my PV equals nRT, is that sufficient for you to tell me the internal energy U of my system? And the answer is no, right? Okay, one last point, and this one's not particularly interesting, I think, but the book likes to make a point about this, and so I just thought I would point it out. In figure 3.2 of the second edition of Finn, the book really makes out this point about the difference between work and heat, right? And their point really is that heat comes from a temperature difference, right? Heat is that energy that flows from a temperature difference. And so they said, you know, what if you imagine you have a gas, right? And you have a heater, and you have some, battery, right? So let's have a battery, and it's going to run some heat across the heater. So whether or not you define it as heat or define it as work depends on where you define your system. So if this is your boundary, right? And so that this is your system, then here you would generate your temperature difference out here, and heat would flow across your boundary. You would have heat flowing, Q dot, right? But the book likes to point out that if instead you had your resistance, right, you had your battery, you had your gas, and then you defined your system as including both of those, then this thing would be doing, there's no temperature difference inside your system, and so there would be doing work. So this is, they think of as dissipative work, and this is as heat. I think that's really a dumb way of thinking about it, personally. I think you should just skip this kind of definition, right, and just think about the system like this and having your temperature flow in. Okay, read that section though in the book if you're interested in more details. All right, we're going to stop here and then we're going to go on and we're going to talk about the heat in isobaric and isochoric processes in particular.